So in this section of the video, we're going to look at the channel options for A and B. And so let's go to our PicoScope. So this is the area in here. So we're just going to look at channel A for the time being. And so if I open up A, and you'll see these four tabs: vertical, probes, DSP, and display. So let's just go to our presentation. The first thing we want to look at is the probes tab. Now it's better if you look at the presentation on the TA386x1x10 scope probes, because it goes into a lot of detail about the probes that have been used, the settings that we're using, and what's the difference between ×1 and ×10. But I'm using ×10 on my settings here. So the first thing I'm going to look at is the probes tab, and I'm going to set my probes to ×10. And I'm going to do it both on my channel A, and I'm also going to do it on my channel B. So standard. And so this is the first thing I want to do when I'm setting up my scope, to make sure that the scope and the probes are matched. So let's go back to our presentation. And so we're going to look at the vertical. We're going to look at the channel control, which is off, manual, and auto. So here is the channel control, and this is on the vertical tab, off, manual, and auto. So if I switch it off, then I lose my signal altogether, which is great. So I can actually choose whether I want to look at channel A or channel B. So because sometimes there's just too many signals, you just want to switch one off. And so that gives me the ability. So I could actually switch channel B on here, and I could put that onto manual. And there's the red marker here for channel B, but equally I can turn that off and go back to my channel A, and there we are, and I've got the blue. Now you'll notice these are color coded, so blue is the default for channel A and red is the default for channel B. So what we're going to do first is select a signal. Now at the University of Leeds, we actually disable the auto function because it stops people from truly understanding what signals they're actually looking at. Because the problem with auto is it will pick up whatever signal you give it and try and work out the best voltage range for that signal based on a time base that you're using. That's the auto for this section. However, there is an auto set up here which actually also adjusts the time base as well to actually change all of this. However, this is purely for the vertical scaling for auto mode. So in general, we try and suggest to students they actually think about the signal they're actually going to monitor and adjust the scope accordingly. So in this case, I have a 1 kHz signal with 1 volt peak to peak with no offset. And so I'm going to switch that on. And you'll see here first, because the scope is defaulted to plus or minus 10 volts, we've got a tiny signal here. And what you're seeing here with these little steps is a quantization. This is a an 8-bit resolution that's on here. That gives us 256 steps. And this is the quantization that you're seeing here. And this looks worse when it's actually, when the signal is very small like this, than it will do if I change my my vertical scale here. Now we've got a signal which is 1 volt peak to peak, so I could use plus or minus 1 volts like this, and once it gets itself sorted out, there we go. Now then, what you'll notice here, so it's looking like a sine wave, which is exactly what it is, and you'll notice that the signal is wandering around a bit. So why is that? Well, this is to do with the triggering. Now there's a separate video on triggering, because it's a really important thing to understand about scopes, is the triggering, and it's so valuable if you understand triggering, control triggering to do what you want it to do. So there are two ways of adjusting the triggering to get this signal stable. And the reason it's not stable is because the scope is looking for a trigger at 1 volt. The signal doesn't pass through 1 volt, therefore the scope can't capture the signal properly. And so it's not synced to the trigger. But if I touch on this trigger and left mouse and then pull it down, I can draw it into the area of my signal, and now you will see it's triggering regularly, and it's now stabilized the signal. So you can actually change that point there by actually going into the trigger menu here, which we'll discuss later on. But primarily this is another video, separate video. We can, in fact, actually what I might do is just show you now, just briefly. If I go into the trigger you'll now see that you can trigger on different types of edges, which I will go into in another video. But the most important thing here is the threshold. And you'll see now, because I've moved this icon to the 0 level, then it's actually showing me the 0 volts here. If I change this value, if I can change it here, for example, and I can change this to 0.2 volts, and enter, you'll now see it's changed the position to 0.2 volts, and the signal is now still triggering, which is great. But in general, if it's an AC signal, it's really good to set this up to 0, like that, and it'll capture and lock in place and therefore sync the waveform. Now, what about using auto? Well, now that we've got a signal on a scope, let's say, for example, I increase the size of this sine wave, and so I'm going to increase it to 5 volts. So let me just go to my parameters, amplitude, 5 volts, peak to peak. Now you will see that I've got a signal, and because this is in manual mode, it doesn't automatically change the scaling. And so I've got a choice of either changing it manually, or this is where the auto is really good, because I could now use the auto to actually now get this so it's no longer out of range. So if I go into auto, it's now changed the signal level, and it's automatically told me it's now gone to plus or minus 5 volts, which you can see on the scaling here, which is great. So auto is useful when you've already got a signal, if you just want to tidy up your screen a little bit. But equally, in my opinion, it's always best to truly understand what these actually mean and how you're in control of the scope, rather than using an auto function, which doesn't necessarily mean that it's actually looking, it's looking at the signal you've got. The thing is that you might think you've got a signal because the scope is showing something, but it could actually just be noise picked up from the mains, because you think you're looking at an AC signal, but it's actually not connected to anything. I've seen this. I've seen students do this. They've got the probe lying around on the table, and they've got a sine wave, and think, oh yeah, great, I got a signal, and they're trying to look at the signal, but it's actually, and that's because they used auto, and so they've auto scaled, but it's actually picking up mains hum, and so they're not looking at any signal at all, but they think they are, and this is why auto can be a bit of a disadvantage at times. So this is why it's best to understand what you're doing, but not understand what you're doing. This is why if you're in manual mode, you can't go wrong. Okay, so let's go back to our presentation here. So we've looked briefly at off, manual, and auto. So we've got the voltage vertical range, which we actually looked at in a bit of detail as well. And so the coupling mode. So let's go and look at the coupling mode. Now, the coupling mode, this is a subject in its own right anyway, so there will be a separate video on AC and DC coupling. But fundamentally, if you want to see a signal for what it is, with all its components, then put your scope to DC coupling, because it shows you exactly what you're seeing. Okay. Whereas if you go to AC coupling, it gets rid of all DC components. And therefore, if you're looking at a digital waveform and you've got it on AC coupling, you will not see what's really there. AC coupling is great for waveforms that are actually truly AC signals, and it gets rid of any DC component. But if you want to know what's really there, then always stick to DC coupling. So I would recommend the DC coupling, and this is one of the reasons why default is on DC coupling, but I will do a separate video on the couplings so that you fully understand what's going on there. Okay, so what about the, let's go on to the next bit, which is the invert. So let's have a little look at that. So the invert, it's really hard. If I do invert on this, it doesn't really make a huge amount of sense. If I invert this signal, I can invert it, and you'll see it's sort of like change, but it's not really obvious what it's done. So I'm just going to put the invert off for the time being, and I'm going to change to my channel B, because I've got a different signal on channel B. So I'm going to turn this, I'm going to turn channel A off, and then go to channel B, and I'm going to put this into manual mode first, and I'm going to switch on channel B, and yes, wow, what's going on here? So there's two things about this. If I go to auto now, the auto is fixing the vertical range, but what it hasn't done is it hasn't changed the time base. Now this signal is at 1 megahertz. Now look at the signal at the moment. It's for 1 millisecond per division, which is great for a 1 kilohertz signal, but not very good for a 1 megahertz signal. So I'm going to go into the time base briefly here, and I'm going to change this to 1 microsecond, and now we can see our waveform. Now the triggering on this you'll see is sitting at 0 volts, and the reason it is actually triggering is because of the noise on this. And you see this this overshoot here, and the trigger circuit is picking up the overshoot, and it's actually locking this signal in place, which is convenient for what we're doing at the moment. So what I'm now going to do is go back into our channel B, and we're going to go and turn on the invert. So invert, when I switch this on, you will now see that rather than a signal going from 0 to 5 volts, it's now going from 0 to -5 volts. And invert is a really useful feature, not so much in digital circuitry, but it is very useful in analog circuitry when you're looking at sine waves, because it allows you to look at the phase shift in quite a lot of detail. When you might have an op-amp, for example, which is an inverting op-amp, but you want to look at how much the phase is shifted, and therefore by using the invert on an input on the output channel, then use invert, you can match two waveforms together to see what's going on. So it does have a lot of uses, but not very useful really on digital circuitry where you've got signals going from 0 to 5 volts. But I'm sure maybe some of you come across an example where, oh yeah, that's a really good thing to be able to do. But anyway, what I'm doing is demonstrating what the invert does. Okay, so I'm just going to turn the invert off here. Now, you can also apply a DC offset. Now, this signal I've got coming in here is a 0 to 5 volt signal, it's a square wave, and the square wave's actually already got a 2.5 volt offset on it, and that's what allows it to wander around from 0 to 5 volts. Now I can add an additional offset to this actually with the oscilloscope. So I could actually put 1 volt in here, and you'll now see that that waveform has now had an offset of 1 volt applied to it. Exactly when you would do this within an analytical environment, really hard to know, but there are times when it's actually relevant. What you will notice now is the waveform isn't locked because we're outside our trigger. Our trigger was at 0, but of course the waveform is now out of range. And so if I now take my trigger point and move this up here, we can now lock it so that the trigger point is now in the midpoint of our waveform-ish, and therefore it locks the signal. So we can see the pre-signal and the post-signal against that trigger point. So that's the DC offset. And also just something to show you here as well is that you can actually change the position of this waveform, which I might as well do now actually and show you this. So if you touch onto the 0 here, you'll just see the icon on the left hand side here, and if I move this up, I can actually move this waveform to different positions. So this is not adding an offset to the signal. This is just a visual offset to move your signal further up your screen. Now this is really beneficial if you've got two signals and you want to separate them. So you now see I've got my two waveforms here. So one is the red one is a DC, as like a digital square wave type waveform, and the other one's an AC one. So you may actually not want these waveforms on top of each other like this. So what's a nice thing to do is you can move this waveform by using this cursor control, and I can now move this waveform up to maybe this position. And equally on this side, this is my channel 2, I can take the 0 point here and I can bring this waveform down here. So now I can actually separate out my waveforms just by controlling the position on the screen. Now remember, this is not a DC offset. It's got nothing to do with that. This is about just moving the relative position on the screen for display so I can separate out my waveforms. Sometimes it's good to have them totally superimposed on each other, depending on what you're doing. But this at least allows you to actually separate out these screens. So let me just come in here. So the DC offset we've actually had a look at. 0 channel offset. This last bit here I talk about in detail in the TA386 scope probe video. So we can have a look at it there. This is what you do when you're calibrating and setting up for the very first time, or when you start up for the day when you're doing your electronics, if you want accurate readings, okay? Because this is all about calibration. And so let me look at DSP here. So from a DSP perspective, this is this tab here. Once again, this is a video all on its own, and we'll talk about that at a later date. And let's have a look at the display section of the name, color, scale, and offset. So let's have a look at that. Go to display. So I can actually now change the color, although these are the default colors, and the little marker sleeves are also the default colors that you get. So you may not want to change these, but depending on how your eyes work and whether you strain your eyes, you may wish to change the color. So you could actually change the color by pulling up the color tab and changing these to different colors as shown here. So you can just change those. Equally, the name, this is channel A. I can change this to another name, IO pin 1, yes? And so that becomes IO pin 1. And so when we're saving information or we're making notes about things, then it just helps us a little bit more about making sure that we're annotating things that actually have relevance to the circuits we're working with. There's also a scaling factor here. Let me just put that back onto A whilst I'm here. So we can change the scaling and we can change the offset here. Now this offset here is no different from the positioning here. So as you'll see, if I bring this waveform down to this point, you'll see that's got 0% offset. So this is a positive and negative number. So this is coming up here. Whoops, there's the 0, so that's a 30% offset. And similarly, I can come down here and go the other way, and you'll see it's a negative offset. So you can actually do the offset rather than using the cursor control to do this. You can actually physically put that in. And once again, we could scale this as well and put in a different multiplier to change this. So if I change this to ×2, it's changed the scaling here, so we can actually look at it in a lot more detail. So I'd have to you'll notice it doesn't do overrange now. It doesn't tell you the signal's overrange. If you're actually wanted to look at your signal in a little bit more detail, this is where you would actually start using the scaling features that are available here. Okay, but as I said, this is a very, very quick look at what's going on from just getting your signals up and running and be able to monitor signals. So let me just stop this video here, and then we'll look at the last bit.